Now, what is current? Current is the movement of charge, but it's not any movement of charge. Current is when you have a net movement of charge in a wire, in a conductor, in anything. Current is simply a net movement of charge. Now, generally, we say that it's the movement of charge, but then we remind ourselves that current results from drift velocity. And drift velocity is when conduction electrons are moving in one direction more so than the opposite direction. If there was no drift velocity, then there would be no net movement of charge. If there was no drift velocity, there would be zero net movement of charge, and thus the conduction electrons would move in opposite directions in equal frequency, and thus you'll have no current. You'll have, in other words, no visible movement of charge. It's like force, right? We may say that something is the act of having a force on another thing. Now, to have a force on another thing and to have an effect from that force, you can't have an opposite force that's equal in magnitude playing a role, because then you really have no force that's having an effect. So we speak of net force. Same thing here. We're speaking of net movement of charge. Now, mathematically, first of all, we denote current by the letter I, and mathematically, I is equal to the charge that moves in a unit time. So Q over change in T, or Q over T. So I is equal, we could say delta Q over delta T, amount of charge over time, coulombs over seconds. Now, there is a special name for there's a special unit for current, and that is amperes, or the one-letter abbreviation A. But what causes that drift velocity? What causes the conduction electrons to move in one direction more often than the opposite direction? The answer to that can be one of either two things. They're really the same thing, it's just that you can look at it in different ways. You could say that an electric field is causing the conduction electrons to move in one direction rather than the other. And in this case, remember that we think of electric fields as pushing away positive charges. So in this case, because by convention we think of the conduction electrons, notice they're conduction electrons, they're negative, but we think of current as having a positive charge. When we think of the movement of current, we think of it as having a positive charge, despite the fact that it's almost always electrons that are moving. But by convention, we think of positive charge. So in this case, the electric field must be pointing, if current is the movement of positive charge, net movement of positive charge, then the electric field must be pointing in the same way as the current, because the electric field moves away the positive charges. And so it would move away the current, so that the current and the electric field are parallel. So we could say that the drift velocity is caused by the electric field moving in the opposite direction of the conduction electrons, but in the same direction as the current. We could say that. And we could say that it is caused by the electrical potential difference, or the voltage, formed by an EMF source, such as a battery. And this voltage, which exists between ends of a wire, influences the electrons, the conduction electrons, to move from regions of high electrical potential to regions of low electrical potential. Right? So we could say, so what causes the drift velocity, which causes the current? Well, we could say it's the electric field moving in the opposite direction of the conduction electrons. Or we could say that it's the voltage, or the electrical potential difference between the ends of a wire, which causes the conduction electrons to move from regions of a high electrical potential to regions of low electrical potential. Now, the voltage, or the electrical potential difference, in the context of circuits and currents, is is referred to as the electromotive force, but in fact it's not a force, but we refer to it as electromotive force. And this electromotive force, which is the same as the voltage or the electrical potential difference, which is found in a battery or any other source of an EMF, of an electromotive force, this EMF is caused by either magnetism or chemical processes. In the case of a battery, it's chemical processes. And this chemical process influences the move of the charge from low to high potential, electrical potential inside the source, inside the battery. Outside the battery, in the wires, the current is going to move, the conduction electrons are going to move from the high potential energy to the low electrical potential energy. Once we get to the low electrical potential energy, how do we get it back to the high electrical potential energy so it can move again to the low electrical potential energy? We do that by using the electromotive force, which is a bunch of chemical processes that moves these conduction electrons from the low to the high electrical potential. Now the influence that moves the charge from the low potential electrical potential to the high electrical potential inside the battery, in ideal situations, quote unquote ideal situations, is equivalent to the voltage difference. Now the voltage difference moves the conduction electrons from regions of high electrical potential to regions of low electrical potential energy. But the EMF moves it from the low to the high, and ideally these two opposite forces are equal in magnitude. So the terminal voltage is what we call, this is the voltage on the outside that causes the conduction electrons to move from high to low electrical potential. This causes the potential drop, we say, is ideally equivalent to the potential gain inside the battery, which happens inside the battery. But this is only in ideal situations, in an ideal source of an EMF, which assumes that there is no internal resistance within the EMF source. This assumes that there is resistance outside, outside where the current moves from the high to the low potential difference. There is resistance. And this is why the terminal voltage, we say, is equal to the current times the resistance. So in ideal sources, we assume that there is an outside resistance, but we say that there is no internal resistance inside the battery, inside the EMF source. But in real sources, there is indeed internal resistance, which is denoted by non-capital letter R. And so terminal voltage in non-ideal sources, in real sources, is not equal to the EMF. It's equal to the EMF minus I times R, minus the internal resistance. Which means that the EMF, the EMF which provides the influence to move the conduction electrons from a low electrical potential to a high electrical potential is actually larger than the terminal voltage. Now keep in mind the terminal voltage is still equal to the current times the outside resistance. It's just not equal to the EMF. The EMF is larger because there is an internal resistance. There's an internal resistance to the there's an internal resistance. Now the fact that the terminal voltage is equal to I times capital R, to the current times the outside external resistance, and the fact that the terminal voltage in relation to the EMF is equal to the EMF minus the current times the internal resistance to that current allows us to create an equation for I. And this equation is the following. If we set IR equal to the EMF minus IR, we could say that I is equal to the EMF over capital letter R plus little letter r.